Okay, let everyone in.
Yep.
Oh, there it goes.
Is on.
Hello. All right. The moderators are here. Our speaker is here. People have drinks. Awesome.
Welcome, everyone.
I've got something.
Oh,
Oh,
Yeah,
Mike's got
just-
something nice there.
Yes, we're researching the Balmer Peak tonight.
Hey, Cecile. Hey, Yoshiki.
We can just chat for a while people dribble in.
Yeah, let's give it a few
Yeah.
minutes. You could start your countdown again.
That's true. Could use my face for that.
yeah. What else are faces for?
You should move it down so it looks like glasses.
Oh, yeah, I'd have to recompile it, unfortunately.
And plus, you only have 2 eyes. You need 4 eyes to do it really right.
Yeah, I
Right,
want to
right.
composite a bunch of these filters at once.
Uh-huh.
I should be wearing fuzzy pink glasses at the same time.
Right.
So I had to go back to the meetup group to figure out how to spell 3 + 4.
It's not that simple, yeah.
It's like which one's symbolic and which one's in Latin letters.
I removed all the keys from my keyboard except for a copy and paste.
Oh yeah, I totally applaud that. Yeah. I will say the name of the group is not legal small talk syntax. So
Oh, well.
It's not? That should parse as 3 with unary plus 4.
actually, I don't know. Don't you need a space
It
between?
might need a space, yes.
Otherwise, it's going to try to interpret the P as some kind of weird exponent.
Uh-huh.
I actually had a bug once where I hung the VM due to floating point format. So basically, I had like a scanner and something was messed up with the pointer. So it's trying to parse some random data as Smalltalk code, and it just landed into this like ASCII armored blob that it started getting digits and then a D and then more digits. And so it looked like it was a floating point number with a ridiculously large exponent. And basically, every time it did a doubling of the exponent to calculate it, it got trapped inside large integer primitive an extra long time before it could actually accept the interrupt. It's very weird.
Mm-hmm. That sounds like a fun thing. Does anyone have lightning talks? Like, we're going to start the meeting with lightning talks. So if anyone has those...
Well, I could turn what I just did into lightning talk. So it's kind of irritating having a small talk primitive that completely blocks the VM for a long time. So I thought it'd be kind of cool having like a new class of integers called huge integers that spill over from, so large integer multiplication will take a bounded amount of time, that it spills over to a huge integer that does some kind of concurrent C call out and only blocks the thread instead of the entire VM. There, that's my lightning talk.
There you go.
Thank you. I think I need a drink for that.
Cheers. Here's to real time.
Yeah, needing to not block critical operations takes me back to when I was first getting BitBlit to run. And I got it to run. It was doing great for everything, text and lines. But if you gave it a sufficiently large thing to do in various ways, it would hang the other tasks on the alto, which was partly bad but it might come back if it was in your interpreter. But if you hold it off long enough in the alto actually needs to take a task to refresh the memory chips.
Oh, that's right. Yeah.
And that killed it dead, as they used to say.
The one that drove me nuts was the drag rect, because it certainly doesn't need to block the VM, but
Yeah.
Wouldn't the video be enough to refresh the memory? Because most of the computers that I designed don't have an explicit refresh because the video does it.
Yeah.
But you can turn off the video on the alto, right, to get a little bit more speed, like in the old Sinclair ZX81.
Yeah, well, so the alto was performing the video in the same way that it was performing the memory. It just ran through more memory chips. Yeah.
All right. If you had more than one bank in the alto, then the video would only refresh that bank and not the rest. Yeah.
Yep.
I was thinking about the first alto that I think only had one bank, but with 512K, that wouldn't work anymore.
Yeah, and also the video is only running through part of the memory, so that it didn't take care of keeping your program alive.
It would make for a fairly interestingly weird garbage collection system, though.
Oh, this is great. Now I can measure exactly the lag between this meeting and the YouTube stream.
Oh,
Yeah. What do you see? Uh-oh, you just got muted, Craig.
If I tell you, then the answer will come to you at the wrong time. So I can't really answer that. So I missed that. You got Reflector working, Vanessa?
yes. Actually, wait, the link in the meetup is wrong. It links to the old, last month's cast.
I just refreshed it.
Oh, I haven't reloaded. So,
I mean, hours ago.
Well, gee, I hope we don't have 40 other people there.
no, I'm on the link for today, and the video goes to Dan's presentation.
Huh. I have no control over that. I just copied the link that YouTube gave me for the stream I'm doing right now.
So is the last meeting up on YouTube?
Yeah.
Yep.
Oh, and also, I thought you mentioned I didn't get a chance to copy the transcripts. Let's see. Any way you can just throw those into the chat, or is it on the meetup page?
Everything's on the meetup page.
Okay.
Okay, let me check again.
I guess we should be checking our emails in case people are out in the weeds and having trouble getting in.
Well, this meeting is nowhere near full, so
yeah,
I haven't encountered anyone yet who prefers YouTube over this.
Yeah, no, I wouldn't think so.
Yeah, the link, the YouTube link is the same for the last event and for this one. on the meetup page.
Okay. YouTube has made a mistake somehow. I can't fix it.
But you're saying you are watching the YouTube.
Well, through the studio interface that only I can see, yeah. And there's a part of that UI that lets you copy the link that other people should be able to use to see the stream.
Mm-hmm.
And the answer it gave me was what it used for Dan's event, which should be a separate stream. So I don't know.
Well, I hope it doesn't overwrite Dan's.
Well,
Art is not eternal.
I doubt it. And I've also got the actual bits on my machine here anyway. So
Oh yeah.
I want to redo it anyway.
I'm going to edit these down anyway. So yeah.
Yeah, we keep saying this.
I've only been saying it for 9 days, so
Yeah.
I feel pretty good about it.
I think I've been saying it for 2 weeks.
All right. Did we set a time when we are actually starting?
My face says 0, so that seems good.
I think that's pretty much it. Well, I guess I can start off and just say, but I may miss some things because one thing that we wanted to allow time for at the beginning of these meetings is for the opportunity to do a lightning talk or two, and we have time available for that. Generally, it'll work best as we go forward if people let us know, sort of about anything that they'd like to see on the agenda, which would include, say, a chance to do a lightning talk. And of course, any desire to see future talks, whether short or long, and or to give future talks.
Mm-hmm.
And I don't know, do we have any such contributions for the agenda at this point?
Yes, I can give it a little lightning talk. I think Craig also had one.
Awesome.
Right. Anyone else? Just put it in a chat, like raise your hand if you want to have 2 minutes or so to say something, show something. Hi, I'm Vanessa. The three of us, Craig and Dan, are hosting these meetups, California Smalltalker meetups. Welcome, everyone. And yeah, maybe Craig, do you want to start?
Sure. Mine is real quick. Just have to figure out the screen sharing thing again. I have to give it some credentials. This delay brought to you by macOS. No way am I going to restart that. Okay. And yet it works anyway. That's disturbing. Okay. I'll share this one. So
Yeah,
I
that works.
got Squeak.js working as a Visual Studio Code extension. So now I'm thinking of use cases.
Does everyone know what Visual Studio Code is?
Visual Studio Code is Microsoft's latest incarnation of its multi-language IDE, Visual Studio. This is sort of a web version of Visual Studio. It's done as an Electron app, and you can write extensions for it in this sort of Node.js framework they have for doing it. And it's wildly popular. It's probably the best thing Microsoft has done. It's got tons of developers using it in many different languages. and I've been using it on a project that mixes a couple of different languages. And just like my reaction to the dev tools built into most web browsers, I think it could benefit at least from a more visually articulate user interface, something that has actual windows that you can arrange how you like to look at long-lived things like objects you're inspecting during a debugging session. And so I think VS Code could benefit from that too, and probably I could do a lot of other weird things with it. That's kind of what I'm thinking now. What could I do with all this power? Just like in the Chrome DevTools, VS Code gives you APIs for manipulating almost everything about the IDE. So I could imagine this being an interesting accessory for doing development in other languages, making more powerful editors that do various things in this IDE. So yeah, it's an interesting new beginning, or a new front for Squeak.js.
That looks cool. I want that. I'm using Visual Studio Code almost every day in my actual work, not in my free time. So yeah.
I want to do something here so you see that it's live. Okay, there we go. Yeah, so VS Code also has an extension marketplace. Just like I've put a Squeak.js extension in the Chrome web store, I will also put this in the VS Code extension marketplace.
Nice.
So that's it.
All right. Anyone who wants to know more about that, go to Craig's website. Well, you haven't announced it yet, right?
No. You can find me on Twitter, though. It's my name with every letter doubled. CCRRAAIIGG.
All right. Thank you, Craig. The speaker list is empty, except I promised I would show something. So here we go. Can you put me big? This,
I think each person controls if they see a gallery view or speaker view.
Oh, well, it just changed from, okay. So I just double clicked on me. So hopefully you see me in large. I just have my iPhone here. So when I scroll here, I'm doing screen sharing. Yeah, you see what I'm doing, and the phone is what I'm doing there. So this is just an iPhone, not jailbroken or anything. It's if you go to squeak.js.org, that's the Squeak.js homepage, and I just wanted to show. I clicked on the launcher, and in the launcher we have various image links, including down here. This one, is the latest Squeak release, the 5.3 64-bit release. And when I click this, I downloaded it before, so it's cached in the browser, but that's how long it takes to boot up Squeak 5.3.
Awesome.
And I can zoom in, so I can use 2 fingers. Can you see my fingers? I use 2 fingers to zoom in, or 2 fingers to move around. And I can create a workspace. And just for giggles, I would do the 3 + 4. And then I don't have the Command P, but I can tap 2 fingers, which brings up the menu. And then where's the printed? There. Printed. Okay, that worked. Obviously, but then also the 0, tiny benchmarks, and again 2 finger tap, printed. That should take a little bit longer. And yeah, not too shabby, I would say.
Cool.
That's my lightning talk.
Nice.
Can you make it? Can you make it a little bigger? It's hard.
I can zoom in here.
Yeah. Whoa, awesome. Yeah.
So that's the bytecodes, and the sends are like 100 times slower because sends are not optimized by the JIT. The JIT only optimizes the bytecode loop inside of one method. But yeah, it's useful.
Mm-hmm.
That's great.
Oops, that was the wrong button. There we are. Yeah, if there are no other talks, then I'll hand it to Dan to introduce our speaker.
Sure. Yep. And folks, remember, if you get ideas for future talks that you'd like to give or that you'd like to see, send them along to us in sort of whatever medium's easiest. So we're fortunate to have today Eric Gady, who works at United Lex, and he'll probably talk a little bit about that. He's been doing Smalltalk for about 4 years. I think he got into computers real early and then, got out of them for a bit, and he'll probably talk about that. But he's been working on a library called SafeBet, which is an implementation of the RISC-V base instruction set in Squeak Pharaoh, or Squeak or Pharaoh. So he's going to talk about that, why he did it. And I know that he'd love to hear from us, especially if anybody has particular, knows more about this or has good suggestions for how he's going about it. So I'll let you take it away, Eric.
Okay, thank you. Let me share my presentation here. Is that working?
Yeah.
Looks good.
Okay, great. So, yes, I have started work on a little library here I call SafeBet, which is an implementation of the RISC-V instruction set in Smalltalk. Just to be clear, not the reverse. I have not implemented any kind of Smalltalk on RISC-V. So I'll cut to the chase here a little more about what this is. This is just the unprivileged 32-bit integer instruction set, which is the core of the instruction set. Everything else is described as extensions. The library I have here also includes a few configurations of basic simulated CPUs for this, and of course memory that I simulate as well to go along with it. One of the immediate goals of that low-level part is to have complete binary compatibility with RISC-V. I'll talk about that some more in the problem section at the end. You can find this on GitHub. Here is the link. If you want, I can make these slides available, and you can have the link as well. I did most of the development in Squeak. I've tried my best to make it compatible with Pharaoh. There are some extensions needed because Morphic's a little different. And I also, for anyone who is using gToolkit, I have a package in the repository that adds sort of like inspector views for gToolkit on the instructions that will just work in gToolkit. I won't show those tonight because it's just too much to show. So as Dan said, I'm a researcher at United Lex. United Lex is a legal tech company. And along with a couple of longtime collaborators, we have a small research group there where we're kind of exploring the future of document interaction and computing systems. And we kind of have free reign to look at whatever we want. And we can be quite ambitious if we want to, even for 3 people. And I'll talk a little bit about sort of how that works into this library here in a moment. I've been doing the Smalltalk thing for a little over 4 years. I put 5-ish years here because I'm rounding up. And I want to make the big caveat that I have very limited low-level experience. I've read stuff online, and I've taken this one course that had me build, a very simple computer from the logic gates up, but I'm not a person who has had like industrial experience with real processors doing low-level stuff. So a big part of doing this, and particularly doing it in the Smalltalk environment, was that I was going to learn by constructing it myself. And so far, that's gone pretty well. And my main motivation, of course, is just that I was curious about it. That's why I started doing it. I started this before the United Lex work, and it turns out it's going to fit in nicely with some of that. But also, sometimes when I'm working in Smalltalk, I think about what would be useful for other people. Now, I don't know if this library will ultimately end up being useful, but I do know that one of the most annoying things to do is grunt work. And there's a lot of it here. And I was willing to do it because it was part of this learning process for me. So going back to my group's work, what we're really interested in is the idea of computing systems that are potentially could be understood by a single person. It's not outside the realm of possibility. This is a vision I imagine many people here are sympathetic to. And so we said, well, what if we don't have to worry about contemporary or past backward compatibility, and we were going to make a whole new computing system from scratch, right? In the general sense, what would we like? When we were thinking about it, we sort of came to the realization that the most important thing for us in computing is metaphor, and that for a user, if a user is going to be more like a programmer, if that bifurcation is not going to be as strong, then metaphor is really important. And so we sketched out ideas for how you could have layers of metaphors that each reinforce the other, that would comprise the different parts of a system. So this is like a chart of something we were doing. So you could imagine in the desktop environment, you're a user and you're going along, you're doing something in like the Finder, and you say, oh, I need to change something in the Finder, but the thing isn't here that allows me to change it. If you peel back a layer, you realize there's this whole hypercard-like thing, right, where everything is described in the metaphor of cards and stacks and objects. And then once you get far enough with that, you could peel it back, and there's something below it, and you could peel it back all the way down. So the work we're doing at United Lex is primarily here. We decided to start here. And I'm not going to talk about that project tonight, but that's where we do most of our work. This project is relevant to what we were thinking of doing down here. And this is where we thought we could describe the low-level parts of a system as actors, both in the Carl Hewitt sense, but really also in the sense of a metaphor, because if you have these specific the play and the actors is a great metaphor for describing everything else, because you can have a play that's about anything. And we were thinking of things like we'll have like the director is the thing that schedules on processors, and stage manager is like memory management, things like that. But in order to do it, we wanted to have an environment that we could completely control and understand, but one that was also not a toy. And the thing that's nice about RISC-V is that it's a real architecture, and people are really going to make chips out of this some are already, like Sci-Fi. Now, so the real advantage of this architecture, if you talk to some people, is that it's, you don't have to have a license for it. So you can just use it and it's completely open. From my perspective, the biggest advantage is that it's designed for simplicity and extensibility. I can understand it. It takes some work sometimes, but I can understand it. And there's a reason for that, and I'll get to that in a moment. So when we were saying that we wanted to experiment on these systems, everyone was telling us, well, just build on what you already have. But the problem is, if we're going to go down really low, this is what we have to deal with. It's like an archaeology of 40 years of craft and some of this design, and there's a lot there. So, if I want to learn on the computer I have now, which is like an x86 machine, how can I learn the low-level stuff? Well, I have to read this manual that's 5,000 pages long. That's what I'll have to do. So you can say, oh, maybe I can just go the ARM route. There's like Raspberry Pis at this thing. Well, the ARM v8 manual is 8,500 pages long. We can be generous here and say There's a general ARM manual that's 1,100 pages, but it's still a lot. The core parts of the RISC-V instruction set manual total 329 pages. 91 of these pages is for the privileged stuff, which I haven't even started on yet. So mainly what I dealt with, even in doing just this, is these 238 pages that are really well documented and readable and easy to find your way around. This to me was like the biggest advantage, because we can start at a low level, but this is the grown-up thing. It's not a toy. It's going to be real stuff. So I just want to go over a few more things before I launch into a demo so that we're all kind of on the same page here. All the instructions, aside from this one compression extension, they are 32 bits long regardless of whatever extension you have. As I said earlier, what I've implemented is the core, which is the 32-bit integer instruction set. It does basic things for 32-bit integers. Everything else is an extension, including 64-bit and 128-bit integers. It does go up to 128-bit in the spec.
Eric, can I interrupt you for just a sec?
Yes.
Everybody here may be familiar with it, but do you want to just hum a few bars about what is an extension?
Oh, I'm sorry. Yes. So the extension is just descriptions of more types of instructions that you can have. So
Okay.
one of the features of the design here is that the way the core was designed with the opcodes and some of the other configurations is that you can have many, many more possible instructions, and the designers have there's like some ratification process where you propose how to actually do things for like floating point and stuff. But most of these have been finalized now. Mm-hmm. So there's actually a whole core, what that's called the standard extensions, and that includes things like the floating point stuff and multiplication and division. So there is a lot, but when you look at it, the number of instructions in some of these extensions is not huge. It'll be like 8, right? So it's not an enormous thing. I don't know what the core here that I've done is something I probably should have counted, but I think it's like 20 or 30 or something. There's not a lot here.
And if you've got the kernel set, then you're good.
You can do, you can do most of the stuff.
Yeah.
Yeah.
Thanks.
So, does that make sense? Is that good?
And I'm assuming probably for most people.
Okay. And so the spec just describes, the last thing I'll say is the spec describes the CPU. It actually describes multiple cores they call hearts. But these CPU that has 32 registers, and aside from the ABI, they just refer to them this way, X0 to X31. So we have a zero index thing, which, as you can imagine, has been fun to deal with. Okay, just a couple of things before I go into this demo finally. This is the layout for the general types of instructions in the set. These are different fields of bits in the full 32-bit instruction. We're going from right to left. And so if you see the following things, here's what they mean. Opcode is just a way of helping specify which instruction gets run by looking at this little bit field. RD is a 5-bit value that tells you the number of a register that is the destination register for some operation, because the 5 bits will go up to 31. RS1 and RS2, same kind of thing. There's source registers for some kind of operation. Func3 and Func7, these are kind of work hand in hand with the opcode to help further specify which instruction actually gets run. And immediates are integer values that are encoded inside the instruction themselves. So this is for me, has been one of the more complicated parts of this, of doing this, because you can see in some of these types, the immediate value is spread throughout the instruction and you have to reconstruct it. And then of course, sometimes you have to sign extend it and things like this. This, by the way, comes straight out of the manual. So does this, which is a chart that tells you for each type of instruction how to reconstruct its immediate value, right? Immediates are useful for things where you don't want to have to pull a number from another register. It's small enough that you can just have it in the instruction. You save yourself an instruction. It's also how you load constants into a register as well. Okay, so is there any questions at this point? Or should I just jump into showing some of this stuff? Okay, I'll jump in. Can everyone see my squeak?
Yeah.
Okay. So, for this demo, I made a little sort of GUI for some of this stuff so that I could show it a little bit easier. The first example I'm going to show is a program where we load 5 into a register, the number 5. We load 6 into a register. We add them together. We put the value in a third register. It looks like this, and I'll describe some of this in a second. It's not very hard thing. There's only really 3 instructions. The fourth is a break. It tells the simulated CPU to halt. All right, so we're going to load 5, load 6. We're going to add them. We're going to put the 5 in register 1, the 6 in register 2. We're going to put the result in register 3, right? So let me get a CPU here. So I'll take this basic one. And here's my program, so I'll just drop it in. And we'll just step through it. Oh boy, I didn't count on this when I increased my font size. Okay. So there it is, 5, 6, 11, right? So what's really going on here? Well, let me open the program again. Let me just show you these instructions. So what I've done is I've made each instruction its own class. And based on those types that you saw, which were R, J, I, and those various things, they're like intermediate abstract classes that wrap some of the same functionality. And so what you have are these fields in there that comprise the different parts of the instruction. And you can just refer to these by name. So here we're setting RS1, which is a source register for this instruction, which is called add immediate. Add immediate takes an immediate value that's encoded inside of itself and adds it to a source register and then puts it in a destination register. And that's exactly what you're seeing here. We're going to encode immediate 5 into the instruction itself. We're going to set the source register to 0. The interesting thing about register 0 in these systems is that it's always 0. So we're just adding 5 to 0. And we're going to put it in register 1. That's how we load those numbers in the beginning. Right, and we do the same thing with 6. And then we do an add without an immediate, which takes these 2 source registers, pops it in a destination register. Very simple program. Give a shout if you have any questions about that at all. So what I will show you then is how this all came to be and how it's sort of designed. Very quickly, I realized I need to have control of bits in a way that is kind of separate from squeak, because there's this big endian, little endian problem, but then there's also the following problem of, like, a lot of the time, because I'm thinking visually and I'm encoding these bits in binary, I want to use this radix format, right? And I want to say, yeah, 255, but the problem here is that this is also -1 in some context. So in a choose complement context, this is -1. So when I'm passing these numbers around, I need it to be consistent. So what I did is I made everything, including the separate parts of instructions and immediates, of course, this kind of thing called bit field, which knows how to do 2's complement on its bits. A lot of this implementation came from Dave Lewis's 2's complement register. So shout out to him for even making that thing. It's on Squeak Source. It's a big time saver for me. And so what we have then are these instruction parts, which are bit fields. They have indexes of where they start in their host instruction, and they have a name. An immediate part is similar, except it has a second kind of index, which is how to reconstruct its full integer value when you send it the message immediate value. For some instructions, the immediate value will be signed or unsigned. So individually, that needs to be dealt with when each of these instructions. And then basically for the rest of the core, we just have these instructions. Now, I can show you sort of what the key features are here, and you'll see what I've been imagining for how I could have this work with the outside world. So in the tests, I have tests for every single one, and they all have the same kind of basic tests. The most important one in the beginning to really test things was from integer. If I get an integer and I look, regardless of what size it is, and I look at this, it represented as 32 bits, am I going to get a correct instruction as I'd expect? So every test sort of shows you what we expect here from these fields. And then I have a bunch saying this, this equals, I don't know if this is good practice, what I've done with these testing here, but this really helped me out a lot when I was making these. And then of course, the reverse of this is also an important test, which is making sure that when you generate the instruction and have it tell it to represent itself as an integer, that you get what you expect. Same thing. These instructions are also documented here. I tried to take as much as I could from the RISC-V manual and put it in the comments here. That also helps me because I come back and I say, oh, what do I expect from this field or that field here? So we can add 5 to 6. Not that impressive. Looking at a bunch of stuff in the register is not that really impressive either. And we're in Smalltalk here, so I figured, what would be a good demonstration? Well, why don't, I can put as much memory as I want in these fake CPUs here. So why don't I make one that's nice and big and that can support a simulated bitmap display that, I just say that some segment of memory in this CPU is going to be where some bitmap display object is going to read from every however much amount of time. Okay, so let me show you that because I did it. This is my simulated bitmap display. And then, okay, so what I'm going to do here is I'm going to load a pattern into the top register, and I'm going to set a bunch of values like where to start writing to the memory segments that the bitmap reads from. And it's going to, this is a 1-bit display. So each little bit is either a black or a white pixel. And it's just going to keep writing, and it's going to write rows and rows and rows as I step through. And I can show you this program if you want, but you can see it here, just kind of going along. And I can also run this. Let's see what happens here. Yeah, I can just run this automatically with a delay, and you'll see it's just writing to the screen.
Yay.
Yay is right.
It's on the screen.
It's on the screen. And then I thought, well, that's boring. This is just a black thing, and it's just eventually it fills up. If I can actually just run this. I think I can just. Oh, goodness. Sorry, guys. Give this a second. The problem is if I have one of these windows open showing the register values, it's like a subscriber to the CPU object. So now when it runs, it's trying to do all the updates on this thing. Let me see. I might have just locked this up.
So you just need a slippage model.
There we go. So here we go. So it finishes. There you go. Black screen. Oh, I'm sorry. One thing I should mention that I forgot to mention. This is my favorite part of this whole thing for me, and what really helped me do this. The instructions. A program here is just an ordered collection of instruction instances. That's it. And the CPU, you send this ordered collection through a message called Bootstrap, and it just loads it in at memory address 0, one by one into the bytes. It knows how to do that. And then it will start going through and pulling out 4-byte chunks and sending the message, from integer to RV instruction. So it's really loading the thing back in and testing it again at the same time. But the instructions are the ones that execute themselves on the CPU. The CPU has no idea. It just calls this, it just sends this message to each instruction after it makes it. And this has really helped because I can go in and see exactly what's supposed to be happening, right? So in this one, you're branching if the two values are equal. And it's pretty straightforward what's happening here. You jump to where you got to go based on that. So that's all of these have the same thing, and that's also tested. So that was another big part. Getting it to work was about making some of these tests as well. Okay, sorry, I thought I had mentioned that. Yes, so yes, black screen. That's fine, but I think we could do something more interesting. So I made one that loops. Oh God, I hope this works. Let's do this. Let me open the display first. I'll drop this here.
Hey, I see something.
You see something, but this is interesting because it's supposed to be rotating. I wonder if I somehow changing all the sizes of everything did something. But these things normally rotate across the screen. Let me see if this works, or if I kill this thing. No, same issue. Okay, well, I could boot it back up in the smaller view if you want to see it. But what happens is these things fill the whole screen all the way down, and they rotate across the screen because it's just doing these. It's just doing bit shift operations, right? In these registers and
Yeah, maybe start this quick fresh. I would
you want to try that? Okay, let me.
love to see that.
All right, let me see it. See if I can do it. That'd be such a shame because this was just working minutes before. Okay. Let's show squeak. Okay, this should be a little bit harder to see, but it already feels better. Okay. The bitmap with the pattern. There we go. No, something happened. Oh, it's just running really slowly. All right. I have an idea. Guys, we're going to do this the manual way.
Yes, an idea.
That's called the John Maloney demo, right, Daniel? At the end.
Yeah, that's it.
So you're in good company, Eric.
Okay, well, good.
This is always my favorite part of the demo, so thank you.
Yeah.
All right, and then by the way, run and run with delay, they do their own new process. So, oh, you know what helps is putting in a program into the computer.
Oh yeah. Close it down.
Bootstrap.
Bitmap draw program.
It will
rotation.
autocorrect. That's fine.
I think this is the one. Oh yes. Bootstrap, you guys are ahead of me here. Okay. Now let's try this. Nope.
Well, do you see a nice debugging session in your future?
I do. I do. You can see some of it happening at the bottom. See it drawing? Something's getting held up here.
Oh yeah.
But normally it didn't have, because it draws each thing every time. So normally it doesn't have this issue, and it's going very quickly. But if we were to sit here till the next ice age, you would see this thing rotate across the screen. I will have to debug that and get it working.
What was the phrase? Majestic or glacial, or there's a
glacial?
technical term for that? Yeah.
Yeah, majestic.
If you think glaciers are majestic.
Well.
So, okay, well, that's a little bit disappointing because that was my favorite part. Maybe if I killed some of these. Someone's running here. Okay. Well, all right, that's that. So, right, are there any questions at this point? Okay.
Probably. Who wants to go first? I mean, that was impressive.
I just think it's really cool.
Yeah.
Thank you.
And
I can't believe this thing didn't work.
It's usual, kind of from a high level, but so we're able to simulate this instruction set, and it's a fun thing to be able to play around with because of FPGAs and stuff.
Mm-hmm.
And I'm curious, sort of what paths through all of that you might have explored, and where this ends up in something that you might actually be doing or building or doing with your company.
Yeah, so my immediate interest with this would be how low level could I create a system of actors?
Yeah.
And I want the problem. One of the problems today for me is if I want to do low level stuff, I have to look at so much dreck, because what people, first of all, everyone only wants to talk about Linux, and RISC-V has this problem as well. So if you go look for anything that's going to tell you anything useful about RISC-V, they're not thinking about easy stuff. They're thinking, you want to boot Linux on this thing, here's what you need to do, even if you're talking about assemblers and stuff. There's not a lot out there for people that don't care about that. So, But what I do want to explore is like what can I do if I can make my own CPU on here and the different parts, maybe get a display to work someday. I kind of can simulate whatever I want here in the Smalltalk environment, which is nice because it's easy for me to understand that and debug it and everything.
Right.
And then if you can do it and it seems right in here, then you have a good shot at it being binary correct. Now another problem I have is that I haven't been able to find other RISC-V simulators that will accept plain binaries. And I can't find ones that will output them either. So I can't test my own stuff against what someone else tried to do. So if anyone has any advice about that, I would love to hear it. If anyone knows about anything, because like the test for me is to take a program I wrote in here, write it in some other simulator, export it, import it in here, and make sure it works. Then I know I'm not crazy. But yes, low-level actors is going to be my first thing. Once I was going to even start it sooner, but the problem is a lot of things are hard without multiplication and division. So I've also designed myself into a corner, and this is something I wanted to talk with people about when it comes to adding the 64-bit extension. There's this is a little in the weeds, but I'm hoping there's a lot of expertise here, so maybe you guys can, and experience, maybe you guys can help me here. The way that instruction works is when it calls from integer, it looks at the opcode, and then it just goes through each class and calls this, set yourself from the integer without the opcode. So each one has like their own version of this, and they kind of have to, because some have this func3, func7 fields, some don't, and that further specifies which instruction is supposed to be. You can see that here, this IB is for B-type instructions, and it's not. It's an abstract class, and it needs to look at func3 to do all this stuff. But the problem is that somewhere here is like a list that tells you the opcodes to the abstract instruction that then will further determine what it is. My problem that I didn't realize ahead of time is that the 64 instruction set shares some of those opcodes. So I thought they would be unique to just this core part because there's enough of them, but I was wrong. So now I have to rethink this design about how you go from the integer down to then making a concrete instruction. And what I'm afraid is I'm going to have to redo some of this hierarchy here. I don't know if that's a good enough explanation or if anyone has any advice about that.
We have a hand raised from Yoshiki.
Oh, yes.
Yeah, the last part I didn't quite understand, but it sounds like some of the problems can be addressed by using string instead of a number. So, I might write a parser whose input is only like ones and zeros. So my parser would parse ones and zeros and generate your RV instruction.
Mm-hmm.
Also, you can do the reverse, so print out binary. Also, of course, assembler. So for helping the debugging, so to spend a little bit of time to have a string representation of bits to instruction would help. And the last, extension parts, RISC, it's like my 20 years old memory, so it's right. But the extension or the opcode is shared by 32-bit version and 64-bit extensions. And so
yes.
sorry, what? Yeah, what's the actual problem here? It's just opcode. If it's the same value, the pure opcode part is the same, so that the semantics is the same, right?
Well, that's what I thought going in, but so it's sometimes it's shared. So there'll be, for example, if you look at this one, this gives you 32 I type instructions. The I types are the ones that, by the way, my naming here is horrible, but it's just to help me out here. I types are ones that have immediate values encoded inside of themselves. So that one is pretty consistent. Except that, you know, this is an I type. This is has an immediate value. This is the load up or immediate instruction, but it is not a part of this, and it has a separate opcode. So it's not entirely consistent, but they try. What's consistent is the format of the fields mostly, right? This has a RD here, RS here. The immediate is in this many parts of this size here. That will be the same for all of these. So it's pretty consistent, but not always. So there's a lot of little exceptions. Yeah, I don't know if that properly answers your question. I've done some of the 64-bit and it's been okay. I've just run into a roadblock with some of them, and I don't see a non-hacky way around it without redoing some of this stuff.
Mm-hmm. So we had a question from Jay. Jay, do you want to state the question? You're muted.
His question is, what happens if you decode an unrecognized instruction?
That's a good question. I believe it just kind of signals some error. Yeah, invalid. It would, if the opcode is wrong, it'll catch it right away. I guess the rest, I can't remember. I guess the rest of these handle them somehow. We could try to put an incorrect one.
What does the RISC-V spec say if it encounters an illegal opcode?
That is a good question, and I don't know the answer. I would have to consult the very brief 238-page manual.
Yeah, I could suggest making a new instruction that's an illegal opcode instruction, so it can go into the memory, and then if it's ever executed, it could just be self-halt.
Yeah, that's good. That's a good suggestion.
I think the default behavior is halt and catch fire.
Yeah.
How about exit image?
Exit image.
Right.
More like a real CPU.
I think the spec says that it traps, and then they use it for supervisor mode.
Yeah.
So the trap is either bad and you terminate, or expected and you go to supervisor and do the right thing for the extensions.
Mm-hmm.
Whoever asked the illegal instruction.
Was that your question, John, or you want to tag that on?
No, that was
You're next in the list.
Oh, I was going to ask, I misunderstood a little bit. Did you say that the same opcodes will decode to different instructions in 64 mode? So this is why you're having a dictionary lookup problem, because you're looking at fixed integers mapping to fixed instructions?
Yeah, fixed abstract ones, yes.
Okay.
I mean, the part of the way I solved this in the beginning was to take, this is called 32I, for example,
yeah.
But the 64-bit equivalent will just subclass this and have a different name.
Yeah, okay. Because we did kind of the same thing for Intel decode and other stuff, and yeah, you can either subclass, or if it's a mode, because you can use the same instruction and sometimes the processors have different modes. So you could have your dictionary could be aware of which mode you're in which point you look up the same bits, but you return a different instruction because it's keyed off a hidden mode as part of the dictionary and the value that you're looking at. So you might be able to hide it behind an abstraction. It just depends on how clean the decode bits are. Because I think their 64 stuff adds extra parameters, but I'm not 100% sure. Right, an extra parameter in the code in the stream. Anyway, with some rambling.
I think the biggest change that I've come across so far, and I haven't implemented all of it. There's not many more ones. Is that load and store, right? Because here in 32, you load and store words, but now you need something that's twice that. So they have.
Yeah,
but that's not a different encoding unless it's immediate, is it?
No, there are several ways to extend a 32-bit processor to a 64-bit. And for example, MIPS chose one way. So the original add instruction adds 32-bit values, and they have a new add 64-bit instruction with a different opcode. But RISC-V, since they from the start they knew that they were going to have 64 and 128-bit versions, they chose a different path. So the opcode that adds to registers, and for 32 bits, it adds 32-bit 32-bit values. And the same opcode in a 64-bit processor will add 64-bit registers. And they add a new instruction with a different opcode that will add 32-bit values if you still need it. So if you look at what instructions the 64-bit version adds on top of the 32-bit, and the same thing for 128-bit relative to 64, they're the new load and store instructions, like you just said, but they're also add and subtract half registers or 1/4 of a register, depending on what you need. So that's the path that the RISC-V people chose. So most of the instructions, they work almost exactly alike. For example, the shift instructions, left and right. For the 32-bit, you need 5-bit operands to tell you to shift from 0 to 31. But on the 64-bit version, then you need 6-bit operands. And that changes the immediate values a little bit, because you can have shift by a register, but you can also have shift by an immediate value. And so it's not completely clean. It's a little bit of a hack, but it's not too bad either.
So this isn't really quite a question, but I noticed there's a lot of VM implementer types here in the group, which I'm not. But, I've wondered if this is kind of slightly analogous to like when Squeak has a different version of bytecode, how that's done by implementer types and how you keep it in sync with the bytecode emulation that's done within context. I don't even know if that made any sense.
Well, yeah, you mean if you change the instruction set, how do you keep things from going south?
Well, like I know, Squeak's got the whole VM written in slang, but if you're trying to do a new version of the Squeak bytecodes, how that works out, you've got to have both the VM and I don't know if you can do them in parallel, migrate. No, I don't really know how that works. I didn't know if there was an analogous situation for any of you types.
I've only seen it done as a one big atomic switch.
Yeah.
Okay.
Well,
So I've seen it done as an evolution. Over the course of Squeak's history, we changed a bunch of things. We got the first thing just plain going, and then we started doing things. We had to be able to access more instance variables, that kind of stuff. So you can do, but maybe this is what Craig is saying. You can make the change and then you try to run it. And in some cases, you have to save an image and start it up with some test flag in it. So it will run what used to run, but if it encounters the new thing, it will do the right thing. I'm not sure.
Well, with respect to the bytecode set, bytecodes in Smalltalk operate on objects. So the bytecode engine actually has no idea if your small integers are 32 bits or not. So the bytecode itself doesn't know that. There are no 32-bit or 64-bit bytecodes because there is only an add bytecode.
That's true. Yeah.
And that add bytecode will, if it knows the kind of object that are the two operands, like if they're both small integers, then it will just do the small integer add. But if not, then it will actually just send the add message to the receiver, and it doesn't care about what's happening there. So in that sense, the bytecode is not dependent on 32-bit or 64-bit or all that. The interpreter itself, yes, needs to know because the immediate values changed. Immediate values are larger in 64 bits. So you have the immediate floats and you have the immediate integers, you have immediate characters. So that's the, I would say, the execution engine around the interpreter or the JIT compiler. And that, well, JIT compiler has to care a lot more, but the interpreter itself doesn't. So the bytecode didn't change when we switched from 32-bit to 64-bit. It's only the representation of objects that changed.
I realize that the width issue is not analogous, but I meant more just the interpretation of a particular byte value having a particular semantics.
Right.
And immediate's kind of confounded here because in the RISC-V world, immediate means something embedded within the instruction. I guess Squeak has sort of like a load 0, 1, 2, or -1 bytecode, I think.
Mm-hmm.
Yep.
But that's different from what a Smalltalk means by an immediate is like an unboxed object.
Right.
Yeah. The difference in the Smalltalk image, I'm not familiar with how Squeak does it, but in RVM, if you're going to add a new bytecode or change a bytecode's meaning, which you can do with the intent of throwing it away after you've migrated, the complication is your images have to be rewritten typically. So the bytecode change, you can always find an empty one, regen, use the new one as the empty one, make a hole in the old one, sort of a two-step dance. But you still have these images that have these old bytecodes in them, and so you have to rewrite those on the way up, which is easy if they're same width, but you have to rewrite and relink essentially if any bytecodes got wider. So it's one of those.
Everything is late bound. That's kind of cool. Like we did change the bytecode set. Sista is the new bytecode set. Right now, and the way it works is that the compiled method has a 1 bit in the header that says, am I using the old bytecode or the new bytecode? The VM actually understands both bytecodes at the same time. So migrating
when you had a third set,
the image is really just you recompile the methods one by one, and it will either execute using the old bytecode or the new bytecode format.
So the actual compiled down VM can actually interpret two different format of bytecodes and compiled methods.
Exactly. Yeah.
So that does seem like a good way to have a smoother evolution than a giant Big Bang.
Right.
That's great.
Previously, you had to do what you said. You had to transform the image in an offline process. That's how the crew with Dan made the new versions using that image writer thing, right? Which just creates an image from the old image in the new format.
You can do that with multiple bytecode tables where your bit can select, so you can go beyond 1 bit if you want. We would do that for other things like debug set versus fast set versus GC set.
It's a single byte, and we kind of envision that there, like, one is the default set for the current generation of VM, and the other would be whatever the new or the old or an experimental one. Smalltalk X, I think, can switch between Java bytecodes and Smalltalk bytecodes at the same time.
Yeah, essentially, you're making your byte wider by that bit.
Right.
So if you wanted to have 10 extra bits, you could do whatever you liked and select one of many variations. In your case, you're Select the old.
Oh, you mean have one bit in each bytecode?
No. But the way you're modeling it is the way to abstract it is you're thinking of it as a bytecode set plus an extension bit, which selects your bytecode table for your bytecode set because you have 2 bytecode sets active. That's an arbitrary decision of making 1 bit or n bits. So it's like dispatching on an arbitrary 8, 9, 10, 11 bit bytecode, which would then your table space is now as many tables as you like, and then you can have old bytecode, new bytecodes. It's annoying to do because the VM gets slower because you have kind of, bytecodes are nice to dispatch and everything else is a little dumber, but yeah.
Well, you only have to dispatch on the compile method because you're not going to, since there's only one of those bits or extensions, it applies to all the bytes in the method. You couldn't intermix instructions in the same compile method, which would bend my mind.
Yeah, or you could escape. So, which is what a lot of processors do. You have a bytecode that says switch bytecode tables. And then
we probably should give Eric a chance to continue on or to wrap up, depending on where he's at.
Yeah, I do have some final slides, but they might have been mostly things we covered already. So let me just pull it up here. Yes. Are you seeing this? Can you all see? Okay, yes. Right. So I designed myself into a corner there. So this thing with the bytecodes is fairly rigid. So I have to sort of think about it. I don't know what UIs to make use of here. I don't mean these little icons and stuff I was goofing around with. I mean more like the window that had register and values and things like that, or how to point at a current instruction in memory, how to show, like, how do you show a really large memory in Morphic, right? Because eventually it'll get pretty big. Things like that. Those are things I've been thinking about. This issue here about not finding the other simulators, I mentioned that. And about how trying to find tutorials online is, there's a lot of noise out there. But yes, in the future, I plan on finishing 64. If I can do 64, I can do 128, I figure. And then I'll get to the even harder stuff. And the goal is to eventually have all the standard extensions done at some point. I do want to do the comparison. I want to come up with more demos, preferably some that actually work. And if you want to play with it, feel free to post issues and pull requests. I'll respond as fast as I can. And thank you.
All right, thank you.
Thanks, Eric.
About the issue of other simulators, if you look for RISC-V online simulator, you're going to find some 6 or 7 of them. And at least one of them will probably be useful for you.
Yeah, so the problem I have there is almost certainly one of my complete lack of knowledge about these things. I am doing the dumbest possible thing, which is to say, I want to write bytes that are just this binary of these instructions from 0. Apparently, this is not something that people like, or I mean other simulators like, and I need to wrap it in some other kind of format that I don't understand.
No, but if you look at these online simulators that run on your browser, most of them allow you to type hex code or something like that and just run.
Yeah. So one other option is that this is something else I came across, and maybe you guys can help me here too. There's some weird hex format that I've never heard of. That's a text format it's more complicated. To me, it seems like more complicated than it needs to be, but it's, and I can't find documentation for it anywhere. It's like some Microsoft format, and I looked all over the place. But I think there's a couple of simulators that will accept that format. Now I'd have to learn how to do it and produce it from the Squeak side. I can't remember. It's like .hex files, but they're, I don't know what that means.
Yoshiki?
Yes. So the interesting direction is, so the idea is to get to the bottom of the thing, or like a computing system. But then for that matter, the existing instructions architecture, like RISC-V or anything, may not be what you dreamed about, right? Like, those folks at Xerox PARC, they made this micro-codable hardware, and their language-oriented hardware was, basically, no, so their hardware was language-oriented or can be made to be language-oriented. And that's sort of what you might want to try, rather than get however clean it is, taking the existing RISC-V and sort of trying to adjust it to what you really want. And bare CPU doesn't actually do much. Only thing we actually have is electrons flowing from one place to another. And registers and memories, if they are just registers and memories, that's just electrons. And we are not necessarily, unless you are interested in electrons, we are not interested in electron flow. We are interested in a little bit more than that, right? So for something to happen more than electron flow, it needs some support. Like, memory isn't just a memory, but you need to do something more than to store value.
In terms of language-based systems, the Smalltalkers and Lispers often go back to tagged memory architectures. And there are people working on tagged memory extensions within RISC-V.
Yeah, but tagged architecture is still just like optimization. It's still, it may make it a few percent faster, or maybe 20% faster or something, but David Angle will tell us. But that's sort of the way Eric phrased at the beginning. This isn't about a hardware project or such, but it's like an entire computing system project.
Yeah.
But also a learning project.
Yeah.
So some of it's for learning. But I do wonder about that. One of the members of our lab does have all these FPGAs, and he's working on stuff with them. But it's hard to know what to do. I mean, I don't know what else would be different. I don't know. Does the non-volatile memory that's coming out change the game a little bit? Would you have a completely different... Can you do something completely different because of that?
I think Giselle had
a little detour. I'm part of the group that's defining the J extension for RISC-V, which is for Java, JavaScript, and similar languages. That includes Lisp and Smalltalk. Now, the group has mostly focused on cache coherency. So if you have a JIT compilation and the compiler is running on one core, and then you're generating code that's going to get executed by a second core, the way that RISC-V was initially defined doesn't work very well. But we've also talked about tagged architecture. It's in a way that's completely separate from these other. There are two very interesting tagged architecture projects associated with RISC-V. There's the low risk one, and then there's the Cambridge one, Cherry. But we've mostly focused on that. Just this morning, there was an interesting email on the J extension group. It seems that L. Peter Deutsch got interested, and he's joining the group and seeing what has been done. So maybe something interesting will happen in the future, because he had quite a bit of participation in Smalltalk in the 70s and the 80s. So we'll see. But so maybe you, with your experience with this project that you're working on, maybe you find things that are missing and say, oh, if only RISC-V did this, it'd be so much nicer, and it would be something that we might include in the J extension. They've also looked at things like, for example, quickly zeroing a huge region of memory, so that you define, oh, I want to put zeros in this 5 megabyte region, and they think that helps. One of the chair of the J extension, he actually did a project where he had a garbage collector coprocessor. So he had hardware with like 4 RISC-Vs, and then he had another processor that just did garbage collection and nothing else. Unfortunately, he chose a not very good garbage collection. So if you start with a bad algorithm and then you make it at 20% faster, that's you're going to lose out to a better algorithm running on plain hardware. But as a student project, it was a pretty good, interesting thing. So if you run into things that you think that RISC-V should do better, then we're open to suggestions. But like I said, so far the last 2 years have been mostly focused on this cache coherency project, and they got envious because a new feature has been added to ARM. That's called top byte ignore, TBI. So if you set top byte ignore, then instead of the 64-bit addresses, you only get 56-bit addresses, and you can put whatever you want on the top 8 bits. So you can put tags or anything else. And so they wanted to have that in RISC-V. So some people have used that in software, for example, to find bugs in the normal C code running malloc, free, whatever. So whenever they use these tags, and they could detect that you were reusing a region that you hadn't freed or something like that, you're located the same region. So they use it for debugging. They use it for a bunch of things. Except that, of course, for RISC-V, they wanted you to be able to have a generic mask rather than just always the top 8 bits. So you can select a mask, and then those bits get ignored. So you reduce your address space, but then you can use that for software. Of course, we went down this route with the original 68,000 processor from Motorola, which only had a 24 address pins, even though it used 32-bit addresses, and then the original Mac OS stuffed bits there, and then when they needed the bits for the 68020,
so
it broke down.
I'm going to break in here and say it's probably time for us to declare an end to the official time, and then of course we can go on chatting with whatever we want to. Eric, is there any sort of wrap up you'd like to add to that, or?
No, that was about it. Thank you for having me. I appreciate it.
Well, we really appreciate it, and yeah,
that was great. Thanks.
Yeah, thank you.
Yeah, thank you. And we're not going to shut down the meeting. So Yoshki had another question, but are we stopping the recording track or not yet?
I was going to stop the recording at the top of the hour, but I can stop it sooner if people want me to.
Okay, so you can go ahead, everybody. Feel free to leave, but we will continue for another half an hour, right? Is that what you're saying?
Yeah.
Okay.
Yeah,
I will actually have to go. So
yeah, so,
thank you, everyone, for showing up.
thank you.
See you in 4 weeks.
So one comment
you.
is about the learning stuff. I actually did similar, not so similar, but CPU simulator, but more visual. And the interesting part of that one was the trying to show the pipelining. The the like even RISC-V, I think it has like a 5 pipeline stages. So basically 5 things are happening at the same time. So my
Mhm.
sort of visualizer shows like, this part of this instruction is touching this, like, ALU stuff, but this instruction is touching this memory stuff. So at every tick, basically 5 things happen on screen, and it's like a schematic of CPU. It's just like memory and register and ALU having two input and one output, and those things are like a pulsing, like a heart, like 5 things moving, pulsing at the same time, and the tick, 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 it keeps doing it, and yeah. So if you are not, if this simulator isn't going to support like those peripherals and interrupt and those other things, you can go lower to show the pipelining, and that's how one of the ways to show how a modern CPU works.
Mhm.
Well, that's like a clock level simulator, which is a lot more complicated than an instruction level simulator.
It's a little bit, but it can be done over a schematic of, like, CPU. Like ALU is just one thing, and like register is, like Eric was showing, just a array of numbers, and like data flow over line. It's that line sort of pulsates.
Oh yeah, that would be cool.
Yeah.
There is an online one that does that for the RISC. I can't remember what it's called, but I can send a link out. It does. It's a website. It's a little web application. You can do simple programs, and it shows you. It actually shows you the flow of things, and it has the CPU decomposed out into all the, the ALU, and then all
I
these
put the
hidden
link on the
parts.
chat.
Oh, okay.
It might be a different one than what you're thinking, but probably the same one.
No, this is even more intense. This one. Oh boy. Yeah. Right. I'll see if I can.
I cannot tell where to click.
And this thing. Oh well. It's kind of frustrating. But yeah.
Oh, yes.
One thing that.
Sorry, go ahead.
I was just going to mention that as part of the VM Maker tool, for the COG version, which generates binary for different processors, it uses an external simulator for the ARM and for the x86, but it has an internal simulator for the MIPS processor. So I only scanned very quickly that code, so I don't know if it's an interesting example or not, but it might be something that could help you if you look at it, or not. It might actually be.
Mhm.
I have something I'd love to share with you sometime, Eric, which is I went through a really similar process to this in resurrecting an old Smalltalk that ran on the Alto. So I started out with just a pile of bits from the Alto, but I knew that it ran instructions of the Data General Nova mini computer. And it turns out that it's a very, very simple mini computer, and it's essentially a RISC instruction set. And so I wrote, this was, I did it in Lively, although I think of Squeak whenever I'm looking at it. But basically a program that just, it pulls words out of memory and decodes them as instructions and executes them. And then in order to make sense of it for myself while I was working on it, I wrote the reverse thing, which I think somebody suggested you might want to do, which is to be able to decompile the instructions back into text so that you could see what you were looking at.
Mm-hmm.
And I'd be happy to share that or do it sometime as a little lightning talk.
Sure, yeah.
It's just a web page, and it sits out there, and you can run it. And when you run it, it actually you can run Smalltalks. I'll paste it into the chat here.
Now, was that in one of the things in the zoo? In this
Was it in one of the things in the Zoom?
No, the zoo, like the Smalltalk zoo.
Oh,
stuff.
yes, it is. Yep, it's in the
I
zoo.
think I might have seen it. Yeah.
Yeah.
In terms of disassembly, do your instruction objects have some kind of print message that prints out whatever the RISC-V assembly language would look like?
No, but I've been thinking about that because it should be really easy to do.
Yeah, it seems like really easy to do. Then your disassembly would just be, just iterate over your instructions and, print them.
Yeah.
Yep.
It would actually even be very easy to get to an assembler from here, I think. Basically that's what it's like almost there.
Yeah.
But yeah, I thought about that because it was like, wouldn't it be cool if I was showing the instructions as they were executing, and not only did you get the assembly version, but I was even thinking like, just make a text that describes what it's doing, because you could do that too. This is going to put this into the,
Sure.
whatever register. You can just do it for each instruction. It'd be a little bit of work, but
You can even disassemble it with the Smalltalk code that creates the instruction in an assembly comment.
There you go.
yeah. Intense.
Yeah. Yeah, when we got the first Smalltalk going, it was as modern Smalltalks go, it was really lame. But we immediately had fun with doing things like simulation and assembly, all of those things that are hard if you don't have a decent language.
Mm-hmm. Mm-hmm.
I had a quick talk-related question for Dan. So when Eric was showing us the program running, he had this giant memory inspector open. And of course, it's spending most of its time updating the display of the memory inspector rather than actually simulating the CPU. And you mentioned something like slippage. I was just wanting to explain what you meant by slippage.
Well, slippage is it's just a way, basically, think of it as a piece of MVC, model view controller, where you've got a model that wants to run faster than the view.
Yeah.
And so you just tell it to every once in a while, it dumps out enough information for you to update the view, but it can go along at a faster pace.
Mm-hmm.
Okay.
So then, if your view happened to be showing the current state of the bitmap, it would tend to go kerchunk, 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 but it would be valid at each of those chunks, so you get to see the right stuff. And then you can adjust your slippage. You can put a slider down at the bottom. So if you want to, you make a 0 slippage, and you see exactly everything that happens.
Yeah,
like that demo would be, just as compelling at 10 frames per second.
I had a similar issue once. I took a Smalltalk debugger and basically just made it so that it would automatically hit send as fast as it could. And of course, then I had the exact same problem, and it executed a whole 6 bytecodes a second.
Yep.
It's working now.
Oh, you've got it going.
Oh,
Yeah.
It's
cool.
working now.
Yay!
Real time.
I didn't do anything different. So I think when I made my squeak full screen, it did something. I don't know. Okay.
Time
So
for you to implement life in this little engine.
oh yeah, that's a good idea. Didn't even think of that.
Or a 1D cellular automata would be good for a bitmap display too.
Right.
What I got very ambitious a couple of days ago and thought, what I'll do is not only will I have this thing rotating, but I'll put a little cursor there and I'll make buttons that move it around. Then I ended up spending like 3 hours on this and getting nowhere, so I just gave up. It's hard doing some of that stuff. There's too much. The bitmap stuff is hard. I don't have to tell you guys this.
You can't use exclusive OR to draw the cursor because that's patent.
Still?
No, it's probably expired, but it was one of the first software patents. People had been doing it for forever, and somebody got a patent on using exclusive OR to draw things on the screen.
Okay, now I need a drink.
Your first slide about the 40 years of accumulated craft, I coined a phrase for that. I say you can't add simplicity, because people say, oh, let's just add a layer. For example, for the one laptop per child, they had the full Linux underneath. And then they tried to hide the file system by creating something called the journal, so that the children would have their objects associated with each day. So you want to know when you wrote this text, then it's not a file in a directory with a name. You just turn 5 pages back because you wrote it 5 days ago or something like that. And the problem with that is that the underlying thing always, there are cracks, and the underlying complexity always bites you, and it ends up being more complicated.
Leaky abstractions.
Yeah.
Yeah. For example,
they never.
Sorry, go ahead.
Oh, just a joke. They never called it embrace, extend, and simplify. So, the only way is to actually start from a clean slate. But it's hard because, these days, if you start with a clean slate, there's hundreds of standards that you have to be compatible with before people accept your system. So,
yeah.
It used to be a lot simpler.
Well, that's what the whole thing about inventing the future is. You just do something insanely great and then and sort of just beat everybody else to the standard.
or burn the disk pack. Don't worry about supporting other stuff. Do what you want.
Right.
Many times I've wanted to burn everyone else's disk packs. Yeah.
Yeah, one thing that I realized about the Alto is that, like Dan said, it started out life emulating the Nova, so that all their pre-Alto code was running on the Alto, and then started adding stuff, added bitlets, added the bytecode interpreters, and so on. So it was a bridge from the past. So I've always started from scratch, but now I think that I have to build a bridge from what people already have to future. So I want to have Smalltalk with a little window in it that's running Windows 10 with x86 binaries in it. And then they'll look at what's outside that window. If I don't give them that little window, they won't look at the new stuff that I'm doing.
Yeah.
Yeah, so all those, I spent a lot of time at one point reading about a lot of these kind of like attempts for other Smalltalk machines or a way to get the current crop, like the Open Smalltalk VM, to run bare metal. And every project seems to have been abandoned.
Yeah, the Squeaking OS, there was a threshold which they never really crossed, which was the ability to save the image. So you boot Squeaking OS, you run it, you debug stuff in it. Now you press save image. They never really got to that point. There was a crude system where you could send the file, the current image to another computer, and it would save it on its disk. So if they had crossed that threshold, I think that it would have exploded. But before you get that threshold, then you poke it around, and now you go back to your development machine. It's a difference between doing cross development and native development. So Squeaking OS was cross development. You had one machine, and then you changed code, then you saved it, then you created a CD-ROM image, then you booted your target machine, and you'd see it, then you go back. So I think that sometimes it's psychological. If you could cross that threshold, if you could develop in Squeaking OS, then. But I'm pretty sure that I think that there's a newer one that's based on Pharaoh called Cog in OS.
Yeah, that one has also not been updated in a couple of years now. I'm sniffing on GitHub all the time, and when I first came across it a couple of years ago, I was like, I'm gonna see what these guys do because I don't understand it, and then nothing happened.
Yeah.
Now I feel that Cog in OS has lots of needless complications added to Squeaking OS was pretty simple. It had essentially two primitives to Squeak: the ability to read and write any byte or I/O port in memory, and the ability to associate a semaphore with an interrupt. That's it. That's what Squeaking OS is. And then, of course, writing your own PS2 driver, your own Ethernet card driver, stuff like that. But what it does is it just adds these two primitives, so you can read write any I/O port or memory byte, and you can get a semaphore so that your driver is written in Squeak. So when interrupt 5 arrives from the serial port, then some semaphore is activated, and the Squeak code that was sleeping on that wakes up and does the job. So for the Cog in OS, they try to bring more existing tools. So there's this cute little project here, there's this cute other little project here. They try to, in my opinion, it seems a little bit like a step back compared to, a more raw, like you're trying to do, the raw bits.
Mm-hmm.
So the more that you create these dependencies with all these little projects, they help a little bit, but they also get in the way because they're a black box, and sometimes they don't do what you want, and then you're stuck.
Mm-hmm.
Tim, your hand is up. Can't hear you. Now 8x8 thinks you're muted. No, you're not muted, but I still can't hear you. Maybe type it to the chat. Yeah, I mean, Squeak NOS was, halted or whatever you'd like to call it a few times over its life so far. So as long as we can continue it, it's
yeah,
good.
and the times that it was restarted was by people completely unrelated to the people that have worked on it before. So we've had like 4 different teams that have worked on the equipment.
Yeah, so I don't know if abandoned is ever the right word. It's always going to be up to observers to push it forward at some point. Tim, still fighting the microphones.
But Jessel, I take your point. It's one of the first thing you have to do when you get something going is to get something visual effects, because that keeps you excited. But then the next thing you need to do is to figure out how to save the changes you're able to make. And then that becomes the clock of your progress. And so then the quicker you can make that turnaround, the faster you can evolve the project. That's just a bit of basic chemistry there.
I gave a talk about Smalltalk machines at an event in Argentina in 2019. And one point that I made was Smalltalk, lots of things were done in Smalltalk that then later people re-implemented in C or equivalent. But it's easier to re-implement once you see it working. And this is a point that then I think you made it in your paper about the Smalltalk team versus the Mesa team, where they would have the ideas on the whiteboard, and then in the next meeting you'd show it working in Smalltalk, and then so there are these things that in theory are possible. I mean, it would be possible to build all the stuff that have been built in C originally, but it wouldn't have happened. So there are a bunch of things that could be done, but if we have this obstacle, so that every time we want to try an idea, it's going to take 3 hours to see the result. Will we do it?
Javier says in the chat, they actually did get a persistence going based on copy on write.
Okay, right.
Mm-hmm. Yep.
Yeah, I'm seeing Yoshiki's comment in the chat. The sort of related, you guys are probably familiar with it, but I was able to track down the book because I can track down rare used books apparently. I got the recursive book, and it is hilarious. I don't know if you guys have ever read this book. Do you know what I'm talking about? The recursive, recursive with the V.
Okay.
The one. The guys
that
that did it are hilarious. The story about how they the lacerating machine is pushed into a canal somewhere, and the guy who wrote it is a complete smartass, and it's so funny. It's also a little bit insane. What they did seems a little bit crazy, but it was a very fun read.
Huh, I have to check it out.
Yeah, torpedoes.
Who else has a lightning talk? We have time we could fit 3 bolts of lightning in the hour.
I think I'm going to have to bid you all good evening, but it's been great. I really thank you, Eric. It was a lot of fun.
Thank you for hosting me. I appreciate it.
Yeah. Bye.
See ya.
We're still keeping the group open here?
Next time for sure. Yeah, I'm going to stop the recording at the top of the hour, but
okay,
keep the meeting around as long as people are here. Awesome.
So, Smalltalk on a risk. Thor, who remembers that?
David Unger and David Patterson. Actually, it's been renamed as Risk 3 now. Because it came after Risk 1 and 2. And now Sora is now Risk 3. And then the next one that was called Spur, that was a Lisp processor, is Risk 4. And Risk 5 is the current one. So that's how we get Risk 5, by having SOAR be risk-3 and SPUR risk-5.
I didn't know SOAR was in its lineage. Cool.
It was actually the inspiration for Spark.
Oh.
Spark is more derived from SOAR than from risk-1 and 2, although it borrows from all of them. But
I was so disappointed when Spark took out the feature of integer arithmetic that would trap on overflow lower than the high bits, so you could, efficiently do the whole small integer trap trick.
Isn't it still part of Spark? I think.
No, they took it out. If you go, I don't remember when, but if you go look at the Spark manual, it's a little footnote that says, no more.
All right. Well, in Urs Hosso's thesis, he actually measured it and decided that was a bad feature. So there's a paper by him and David Unger from eCoop 95, which says, do object-oriented programming languages need hardware support? Where they found almost the opposite results that they had from the SOAR project.
Is that the same link that someone put in? Yeah, I'm looking at the conference paper. Yep, I see it. Yeah, I got it open ready. Cool.
Now, the problem was on the Spark that they measured, if you tried to add 2 integers in the tag said that they weren't small integers, then you'd trap.
Yeah.
And unfortunately, in that processor, in that version of Spark, in that version of Solaris, it took almost 2,000 clock cycles to handle a trap. So 2 things, and also when you had the register stack, the register windows, when you got an overflow or underflow, you also had the trap that took 2,000 clock cycles.
Yeah.
So
and moved to memory, so it's expensive too.
Yeah, so they decided that these features were bad, but for the Spark version 9, was the 64-bit version, I think, they improved that so there was less than 100 clock cycles to handle a trap. So the results that they would have gotten would be very different. But basically, the huge cost of handling traps made them decide that register windows were bad, that tagged integer were bad, everything was bad. So.
Well, it seems like you could still have specialized hardware support that would do something less draconian than a trap.
Oh yeah.
But even modern implementations don't use tags. Like V8 doesn't tag their integers. They load tag pointers, and all pointer arithmetic is -1, and that means you can just add 2 numbers without subtracting the tag from one of them, and so it is actually faster to just add 2 numbers that are shift lefted by 1.
Lawson, your hand is up.
Yeah, I just wanted to interrupt for a second and ask if anyone could just give a tiny bit of advice. I created a list that took about 20 or 30 minutes to create. It's an ordered collection, and my current workspace has gotten totally cluttered. How can I transfer the reference from the current workspace to a different workspace?
Well, the easy way is just put it in a global variable.
Okay. Because I was looking at things like class bindings and all sorts of stuff, and none of it seemed to work. So,
what do you mean? You have some random large ordered collection somewhere you want to save?
You have an object that's in a workspace. You want to get to another workspace.
Yeah, I created a list of all primes up to 1 billion, which takes a while. And
I get you. VisualWorks actually lets you copy and paste objects between windows, which is kind of cool. But again, the easiest way, and it's really ugly, is just assign it to a global variable and then go to the other workspace, and boom, you've got that global variable because it's global.
Yeah, I was just wondering if there was an easier way than that, because it's just kind of sad.
It is sad. I'm not as familiar with what's been going on in the Squeak development environment as opposed to VisualWorks.
Well, actually, couldn't I just create a something simple like a diction? No, not a dictionary. Just I don't know, an association and just look for all the instances of association with the one that just happens that thing.
You could. That's more horrendous. Scouring through all objects is more horrendous than assigning a global variable. Global variable is very simple. You just type it in, and boom.
Yeah.
We all know it's the wrong thing to do, but then you really shouldn't be programming a workspace, and that's pretty much all I program in these days.
Yeah. Well, I was just experimenting. It's just crap. But I have figured out a way of factoring an arbitrarily large number, but only if it just coincidentally has the right thing. For instance, I found out that 8,192 raised to 1,000,000,001 has a certain factor. I could do it in half a second. Even though I've never factored that particular number because it doesn't fit in any existing computer, I can still tell you that there's a given factor in that number.
Oh, don't get me started on ultra-finitism.
Oops, goodbye, Internet. We're stopping the recording, but please continue.
Yeah. But I'm just playing around with prime numbers, and they can get ludicrously huge,